And now on to the software panel. Interactivity, Tutor, all of the things that are associated with the early days of Plato are going to be the subject of this panel, and it will be moderated by Steve Gilmor. We're very lucky to have Steve here today because 2 months ago, Salesforce.com CEO Mark Benioff bagged the ultimate trophy, I think, which is to get Steve Gilmor to stop doing the wonderful things he's been doing in blogging and writing and podcasting about technology, and to join Salesforce as the head of technical media strategy there. But he is better known to all of us and is highly qualified to be the moderator today because he was the founding editor of TechCrunch IT. TechCrunch is a must-read if you're here in the Valley working on technology. He will continue to write periodically for them. He remains one of the leading commentators on technology, and his career includes filmmaking and recording and music, and he also has been the back page columnist for InfoWeek magazine. Quite a transition from that to what he's doing today. Please welcome Steve Gilmor, and he'll introduce our panel.
Thank you. Well, it's a great pleasure and quite a bit of an honor for me to be here involved with all these people. Just briefly, I have known Ray Ozzie for quite some time now, and to watch him on stage last night with Don Bitzer, looking at him like a cub student is an eye-opener, because that's the way I look at Ray. So I'm very glad to be here and in awe of what you folks have all accomplished over the years. Let me introduce the people on the panel today. Starting to my immediate right is Michael Walker, who, according to this, first met Don Bitzer through a high school engineering club. What was that?
Oh, well, that was the JETS Club, the Junior Engineering Technical Society, and Don was the science advisor, the technical advisor to that club, and we were building a reed switch computer system down in his basement. And well, to tell the story there, in my junior year in high school, I joined that club, and I'd go home after school, deliver my papers, grab a bite to eat, and head to Don Bitzer's basement. And I must say, I'm astonished at the forbearance of Mary Ann Bitzer in putting up with this, because there was stuff going on down there in that basement till sometimes 9:30, 10:30 at night.
Ooh.
running lathes and all this sort of stuff, and she got people drifting through her house, but seemingly oblivious to it. And Don Bitzer hired me as a summer student at $1 an hour the following summer, and I worked at CSL, CERL from that point until the lab was closed in 1994.
All right, well, we'll come back and you're going to give us a little history of all that period of time. Next we have Bruce Sherwood. Dr. Bruce Sherwood is a physicist who contributed to the development of the PLATO system software and was for several years assistant director of the computer-based education research lab at the University of Illinois at Urbana-Champaign, and co-chair with our other panelist, Robert Rader of the System Software Group. So how did you get involved in this?
Well, I was somewhat retarded compared to most of the people who've been presented, because I didn't come into this until I was 30 years old and a little over the hill. But in 1968, while I was a young professor at Caltech doing experimental particle physics work and teaching in the remarkable course that Feynman had produced, I got very interested in the possibilities of using computers in education, which I'd heard about. And I read all I could and visited some of the key centers. And then a mentor back at Purdue, where I'd gone to college, told me there was something going on over at Illinois. And I said, no, there isn't. I've read the literature. There's nothing going on in Illinois. And he said, well, if you're going to go into this field, I think you should just take a look. I don't know exactly, but it's worth a try. So I went over there, and I'll tell you later what happened that day.
Fantastic. And Bob Rader learned about programming and computers as a graduate student in physics in the Alvarez group at Berkeley, worked on elementary particle physics. In other words, you're an actual real genius, right?
No, I'm not.
Well, you were working on it.
But I worked with a lot of them.
And you had a postdoc in a bubble chamber group in Saclay, is that how it's pronounced?
Yes.
France, using the same CDC 6600 computers as at Berkeley, and also, I believe, as are on loan here. And you first saw Don?
I first saw Don giving a talk and demonstration in Geneva at CERN. And I'd been looking around for what I was going to do after my postdoc in France. And here is this guy with this vision, with hardware that was totally novel and doing things that nobody else could do. Clearly a problem solver and a very dynamic, energetic person. If you've ever seen, we ought to have a video of Don giving a demo. And the total thing was just totally impressive, and I said, I've got to really look into this and go find these people.
And you were at a point in your career where you decided you needed to find some place where you could really bootstrap and move to another level.
This looked like a place where one would be really happy and have a lot of fun.
You could get it on the ground floor, greenfield.
Actually, they put me on the top floor.
Okay. Well, I'm not the scientist of the bunch, so I'll let you explain that to me later. So let's go back to the beginnings with Michael. And we've got a few slides, not a lot. If we could just get some history here.
Oh boy, is that visible or not? I just wanted to cover a little bit of the kind of history of the environment in which some of this stuff was taking place, and just give a bit of a description as well, just how unusual as an early time-sharing system PLATO was. In the era, I mean, go back to the late 50s, early 60s, in fact, even well into the middle of 60s, the common academic computing environment was you walked up to a window with a deck of cards, and if you had a lot of data, maybe a couple of magnetic tapes, you handed them through the window, and you had to come back later. And when you would come back later, whether half hour, an hour later, depending on the circumstances, they tended to divide the day up into express runs and somewhat longer ones. You get back a printout and your tapes and your original deck of cards or paper tape that you'd started with. And you can imagine this is really a pretty slow way to do things.
This is kind of analogous to how long it takes for Windows to boot, right?
Oh, well. Yeah, something like that. But stop and think about where that put the incentives. It really, in those early days, and if you were dealing in that kind of environment, put an extreme premium on somebody paying what, to a loosey-goosey person like myself, is an inordinate amount of attention to the detail, because if you had a typo in that thing that you put through the window, you just lost a half an hour. A compiler error, anything of that sort. So in that environment, in that sort of thing, there began to be people thinking, well, there's got to be a better way, let's do time-sharing systems. And the typical academic time-sharing system at the time was really just essentially, instead of handing in paper tape, you're sitting at a teletype. And it's very much a line-oriented system. The very earliest one that I'm able to find on Wikipedia is the compatible time-sharing system running on an IBM 7090, which I think was done at MIT. Wikipedia says the work started in '57, but they never demonstrated until November of '61. PLATO 2, by contrast, the one shown up there, which was 2 terminals running off of ILIAC 1. ILIAC 1 was a vacuum tube machine, basically at the end of its life in that era. 5,000 bytes of memory in that thing, and they did manage to actually run 2 terminals on it and be a time-sharing system with running 2 graphical terminals as opposed to teletypes. back in 1961. That was shown in the spring of 1961. You move up the scale a little bit here, and time-wise, PLATO 3 came online, and I think you've been hearing a lot about high school kids here today, but I want to point out someone. You see, that's pretty early on this time-sharing line here. Andy Hansen, who's sitting down here in the front row, was one of the original Bitzer Boy Scouts, and was really only there for 2 years, maybe 3 at the most. And in the summer of 1962, when the CSL laboratory had just recently gotten a CDC 1604, Don Bitzer assigned Andy Hansen the job of developing a timeshare resident for that thing. It's called Cato Res. There was a second person, Steve Singer, whose job it was to, if I may use the term, bastardize a Fortran compiler at the same time. So what Andy Hansen did in this era, and this is way before its time, design a timeshare system that would run up to 32 terminals. An absolute beautiful piece of work. And he didn't realize until years later that there was anything unusual about this. But in fact, this was a seminal piece of work. Included in this, along with the Cato Res, you could write in Fortran the software for this thing, and the way the compiler and this resident interacted, you could write it as though there were a single terminal there, but it would run up to 20. And all of this stuff was handled automatically by it, and it provided the basis for the very earliest of the PLATO 3 software, and was the foundation for that until Tudor was added to PLATO 3 later into the mid-60s. And if you look on the bottom timeline underneath there, the Dartmouth time-sharing system was a year or two after PLATO 3 really got running. Unix didn't come online until the 1970s. And again, character-oriented, line-oriented kinds of situations on the others, whereas PLATO was running graphics terminals, every key went into the preprocessed, came back out again, so that you could do what were extraordinarily different things in that regard, as opposed to what you're dealing with, a teletype, put in a line, hit carriage return, it chunks for several seconds, and something comes back. We were dealing with 100 millisecond and less response times all the way through this.
Now, was there something about this, I want to bring everybody in on this, occasionally as we go through this timeline. Was there something about, you mentioned Andy's contribution in terms of a sort of a foundational layer on which Tudor was built and some other things. Did either of you folks see something unique at the early stages when you got involved that was representative of this particular part of the history, or was it something else that attracted you to the project?
Implicit in what Michael spoke of was the invention, I think, by Don Bitzer, of reentrant code. And maybe you want to say something specifically about that.
Well, I don't know that Don was the inventor of reentrant code. Maybe he was, but again, this thing was written in a way that indeed the code was reentrant. The resident kept track of all of this stuff for the programmer, if you will. You write the program straight out there. It would run through your sequence of subroutines, keep track of the linkages along the way, and if it had to be interrupted, kept everything saved away properly so that you could then bring in the processing for a different station along the way. And that all happened in a magic way. And Andy, at the time that he wrote that, was 17, 18 years old. And this was yet another example where Don threw a task to a young person, depended on them to come through, and that provided the foundation from PLATO 3, actually I think through the entirety of it, including the Tudor era. Cato Res remained a valuable piece of that. And the other part of this is the emphasis on graphics. And one might wonder, well, and all this other academic computing stuff, you're dealing with line-oriented machines. Why on earth did Don Bitzer think graphics were so important? And I think the reason for that, I don't know if Don would answer yes to this, is he was used to doing real-time processing of radar signals and developing pictures out of that. And I later was shown pictures by Don once they were declassified. It was pretty far into the 60s by then. They were able to take pictures of bridges from 50 miles away using this radar system which you could see the individual light poles on the bridge. And he was also, I believe, they were working on real-time processing, looking at aircraft coming in as all part of the radar lab aspect that had been at the Coordinated Science Lab. He was graphics oriented and understood that point to a degree that was not common in the computing world, except in those circumstances where you could hook a big tube directly up to a computer and use it in that way. And he saw the value of the graphics, wanted to move that out into a broader context, which presented some interesting software challenges along the way.
Bob, were you at all, how old were you when you first started with the project?
Well, I also was, not also, I was, as Bruce, not a high school student at that time. I was in my early 30s when I joined.
So
and much later than the period that Michael is talking about.
Right. There seems to be a common thread of very young people at $1 or $2 an hour. If they had any money at all, working with multi-million-dollar machines.
Well, there's a story there. I mean, I asked people just to think about this. I was being paid $1 an hour, and I was given free rein to access to $1 million machine, and there was no supervisor there. I mean, we were given a key to the door, and it was late at night. You go in there, and I don't know that you could do that today, although finding $1 million computer is a tough thing to do as well. So the openness existed to that point. People, the young kids were just trusted to go in and do important work and not violate the trust. And I think it worked out pretty well in the long run.
All right, so are we done with this slide?
I did want, well, pretty much. I just do want to point out, in the mid-'60s, and I think it's an important feature that came along in terms of this time sharing. Even with the Cato Fortran compiler, and it was possible to write material for which you could run 20 terminals in a very interactive way. But the software development, while it was a lot better writing this stuff in Fortran than it was in assembly language, which is what they'd been doing before then, the real seminal thing that came along to decrease the development cycle. I mean, I talked before about you turn in your cards and it's a half hour later. Well, we got to the point where you could have some pretty good interaction on a much shorter time scale. The development of Tudor in the mid-'60s fed into this time sharing concept to the point where you're talking about turning the turnaround times shrinking down to a matter of seconds and minutes, a very few minutes to do another cycle in your program, which I think led enormously to the explosion of the things that happened there. Even though there was a lot of valuable work done before Tudor came online, including some of the nursing stuff. Roger Johnson talked about his EE322. That was done with the Fortran-based development system. That level of interaction, first with the keys and the terminal, and then eventually also with actually at the programming end of it, is what I believe led to PLATO exploding in the way that it did in terms of its viability. And that carries on into this timeline, into the 70s, when PLATO 4, which was designed for hundreds of graphical terminals on the CDC 6000 series with ECS. Another thing I would make just a point in this time of history, none of these machines had integrated circuits in them at all. These were all discrete component machines, iliac 1 vacuum tubes. The CDC 1604, which PLATO 3 was done on, was the first commercial machine designed by Seymour Cray. He's far more famous for the 6000 series, but the 1604 was a discrete transistor machine as well. A beautiful, elegant piece of work in itself, The 7094 that the University of Illinois had downstairs on the ground floor in what later became the zoo of the Plato classroom took up 3 rooms. Not exactly equivalent computing power, but pretty close, was a 1604 up on the 4th floor. And its footprint, you could put the entirety of the mainframe and its 4 tape units would fit on this stage. So even back in his very first implementation, Seymour Cray was making distinctly different machines that was designed so it could, I believe, fit on a submarine. Whereas the IBM thing, room was not an issue, and it sprawled considerably. So, anyhow, to be done with this, we talk about hundreds of terminals for Plato 4 in the era of the 70s. The Dartmouth time-sharing system did achieve, apparently, according to Wikipedia, upward to 300 terminals in roughly that same era. But again, it was all teletype-oriented. It's never the graphics at that point. So I hope that gives a little bit of a flavor of what things were like in the olden days, and maybe people have questions that come to that later.
Yeah, we're going to have some time for questions in a bit.
So just to reiterate, early time sharing and beginning in the 70s, you're talking about the typical system where you had tens of teletypes running at a few characters per second, line-oriented, and millisecond response times, and swapping from disk at maybe a megabyte per second. And Plato in the 1972 era, we were talking about hundreds of 512 by 512 graphics terminals, 180 characters per second, and again, the single key interaction, which allowed you to do things not just in Roman characters, but you could do many different languages, and you could do things like electrical symbols for circuits, things of that sort. And we were seeking 1/10 of a second response time, and achieving this by swapping out of a very large ECS, a large core storage memory, and that access time is a little long. It was probably closer to 5 microseconds.
Well, you know, this was the birth of RealTime. I think that's pretty clear in retrospect, and you know, particularly now with the rush of cloud computing to the fore, and systems like Facebook, and you know, on and on. It seems like that decision from a goal perspective of 0.1 response time, that probably was the thing that broke this all open. So at the time, was that considered to be the holy grail of what you guys were doing?
Well, there were measurements that Don had made using the Plato 3 system, and you were there at the time, that showed that, at least for educational purposes, you were going to lose the student if something didn't happen when you pushed a button. And so that 1/10 of a second response time became an important goal and a piece of his very clear mission statement. We're going to deliver quality education with high quality graphics and rapid response. And so all of our feet were held to the fire to meet that, and it was met.
And how quickly was it met?
By that time, or even earlier. Even Plato 3.
But from the beginnings of the project, how long did it take you to figure out what you were doing?
Me personally?
No, just in general. I mean, from your understanding of this. I mean, Kennedy said we're going to go to the moon, and it took a while. But, you know, I think
Michael, of the three of us, Michael was the only one who was there from the birth.
Mm-hmm.
Yeah, the response times on Plato 3 were such that you could actually measure this. I mean, it was achieving 50 millisecond response times. So very early in the game. I mean, in 1963, it was able to do that, and that's how they made some of these measurements. And then you could purposefully slow down the response time and to see how people reacted to it. And I think the crucial thing is not that you can fill the entire screen instantaneously, but at least the person needs to have the sense that the computer is serving me. I'm not just waiting here. I mean, and we've all tried loading web pages where you wonder, is this ever going to come out? So it applies even today. You want to have the sense that the computer is responding to you. And in a network system, quick response time, whether you can complete an entire screen in a half a second or not, is less important, in my view, than that you see that something is going on and that it's happening in a quick way.
Something's happening.
Something's happening.
You may not
and it's
know
moving
what.
forward. Yeah.
Right. Or there's the promise that something will happen.
Yeah.
A
In
waiting
fact,
cursor or
some
something.
of us had the experience of running over a satellite link to give a demonstration in a foreign country, and then the response time, just because of the speed of light to a synchronous satellite, was a few tenths of a second. And boy, was it hard to run a PLATO lesson that way, because it was so sluggish.
And because the design of those programs
Also,
assumed a certain response.
right.
Right.
yep.
All right. Let's keep going.
This is a basic display of the PLATO 4 architecture. And so the core of this whole thing was the ECS storage in the middle. And the important thing, if you want fast response time, you got to have everything in memory. But if you see what that ECS, and this is a design for, we're talking here, hundreds of terminals active at the same time, 8 megabytes of storage, which is, by today's standard, practically nothing. Again, the 10 microsecond access is a little slow. It was actually closer to 3 to 5 microseconds. And although initially we did not have this many CPUs, I mean, the system eventually developed to the point where we had 4 CPUs running out of this swapping memory. All the data from the disks ran in through a thing called a side door adapter. So there were peripheral computers, those PPUs, were directing all this stuff, but the data flow was into that swapping memory and back out again. The keys would come in through that side door adapter and stuff back out again. And the way that we were able to achieve the ability to keep to that tenth of a second or less kind of response time was to divide up the tasks. You had the executor, which would execute the Tudor partially through interpretation, partially through stuff that was compiled. But you would pull stuff out of the swapping memory, process on it, put stuff back in the swapping memory. You'd have a formatter here pulling stuff out of it, processing it some additionally, and sticking it back out there. And we tried to divide this up so that you could apply the CPU to the tasks that needed doing in any particular instant in time. So the typical rule of thumb was one formatter could handle the output from 2 executors, and you needed a condenser around to be able to, which the condenser was equivalent of a compiler. I mean, that's the closest analog that you might have there. So this whole structure was set up always keeping things in memory to the absolute degree possible, swap it into the main RAM of the CPUs, which a 6400 like that only had 65,000 words of memory, so 8 times that in terms of bytes. So the actual central memory was tiny by today's standards. And so we'll deal, I think, later a bit more with the way the resources were allocated in this regard. But the trick was to keep everything in memory to the degree possible, go to disk almost never, unless basically if somebody was entering a new lesson or somebody was logging in for the initially, yeah, you pull the stuff in off the disk and keep it in memory from there forward.
Okay.
Now, and this is just kind of a whimsical description of how this stuff was all put together. You had the input coming in, each key coming in one at a time. You see up at the top of the screen the pieces of the lesson piling down in there that were the student variables. And there too, we want to talk about memory requirements. The student variables, by my calculation, represented about 3,000 bytes. That's 3 kilobytes per terminal. Now there were typical lessons also had some of what was called common storage that was shared amongst multiple terminals. So you would get a bit more memory involved. But you really had to code things in a pretty efficient way in order to get along with that minimal amount of memory. But if we tried to do more memory than that, we could never have achieved the kind of response times that we were talking about. This would not have been possible.
Credit Jim Perry made this nice whimsical diagram years ago.
All right, so now we have the hardware software platform instantiated. Now what do you do with it? Let's go to the let's talk about.
Let me pass this off to Bruce here. We'll start talking a little bit of and maybe you want to ask him that question about.
So, to introduce what Paul Tensar's creation of Tutor did for the system, I need to continue my little story of how I was introduced to the PLATO project. In December of '68, I visited PLATO at the urging of my Purdue mentors' urgings, and I got there an hour early for my appointment because I forgot about the time change between Indiana and Illinois. So the secretary gave me some internal reports to read, things that had not been published. And I opened the first one and it says, a modern CDC 6600 could run 4,000 graphics terminals with a 1/10 of a second response time. And I said, what? What are they talking about? Because what I had seen in the world of using computers in education was a few teletypes and slow response and line-oriented and no graphics. And this was like getting a message from outer space. The aliens have arrived. It made no sense. So I'm reading these things, and they're making no sense, except all the numbers work out. I mean, it's all designed there. These are articles by Bitzer and his colleagues. And I couldn't see any holes in the argument. Then this guy comes in, Don Bitzer, and he takes me into a nearby room, and there's a bunch of graphics terminals there. Well, I'd never seen a graphics terminal before, let alone a room full of them, let alone people working with them. But then the really dramatic thing. Here in the corner is sitting somebody who represents something extraordinary. And to explain how extraordinary it was, at one of the major, best-known labs doing work in this area at the time, system programmers were carefully, with great effort, coding up simple arithmetic drills. But here in this room, in December of 1968, was Professor Richard Scanlon of the Classics Department. He was writing his own sophisticated materials on teaching Latin translation. There were no system programmers in the room. He was doing it himself. How could this be? Well, it was because of Paul Tensar's invention. In 1967, Paul could see that given the nature of the hardware and the software, the next bottleneck was how would you in fact write large amounts of material to be used on all those terminals? And the standard ways of doing that were just too expensive, too time consuming. So he created the Tudor language. And I want to show you just a little bit of the flavor of that language to give you a sense of what he achieved and why it was possible for Dick Scanlon, a classics professor, to write his own high-quality materials himself, thereby combining in one person the experienced teacher, the designer of the interaction, the coder of the interaction, and thereby being able to make compromises among all three roles because he was doing the compromising with himself. And this led to a tremendous outpouring of wonderful things. It also led to an outpouring of terrible things. One of the central components of Bitzer's openness was that he structured the hardware and Paul structured the software in such a way as to be completely neutral to any particular educational philosophy. It was truly open. No one was telling you, you must write your program this way because I know how it should be done. And so Scanlon did his thing, and Curtin did her thing, and Smith did his thing, and let 10,000 flowers bloom. And of those 10,000 flowers, probably 1,500 were amazing, and you'll see some of that today. And maybe 8,500 of them were dreck, but that's okay. It was a very, very open system. And so Bitzer and his lab were open not only to young people, but also to old folks like Dick Scanlon, who were welcomed in and said, sure, here, have a seat, write some stuff, see what you can do with it. Well, here's an example. This is a screenshot from Cyber1, the currently running instantiation of the old PLATO system. I'm showing the screenshot black on white because it just projects better. But think orange on black, glowing orange on black. It was very dramatic, but it doesn't project very well. This was around, this would have been early 70s, 71 or something. Paul Tensar created Tudor in 67. I came in that day in 68 when I saw Scanlon writing programs. By the end of the day, I had a job. And I came in there in July of 69. This is just a little bit later than that. This would have been, say, 1970, 71, something like that. I'm in the editor writing a program, but when you pressed one of the keys on the keyboard, the text editor, program editor, was a graphics editor. So actually, using cursor keys, I actually draw that triangle, pick a position for some text, type in the text, what is this figure, and then mark a place where that little arrow-shaped thing should appear. And I'm doing this all graphically, so no code that you see. And then when I say hit back, it actually, from the graphic representation, generates Tudor code. So what you see at the bottom of the page is examples of the Tudor language that Paul created. It was a fixed format language, commands on the left, arguments on the right. The arguments here, you can see their numbers. These are rows and columns. You could also specify in X, Y coordinates. So you see the triangle is represented by a draw statement, go from here to here to here to here and back. You get the triangle at row 26, column 12, or vice versa. Write what is this figure, put a little arrowhead on the screen. Then the next lines, numbered 5 through 8, I had to actually enter by hand. And this is another very unusual feature of the Tudor language due to Paul, answer judging. This language had to meet a lot of unusual design criteria. It had to be easy enough for a classics professor to use. It had to handle graphics at a time when nobody was handling graphics. It had to be able to flexibly process and understand as best it could and respond to student input that may be malformed. So that on line 5 you see answer. It is A in these brackets. Those indicate ignorable words. Then comes right, comma, RT is synonym. Those are synonyms. And then triangle is a word that must be there. And the next statement, the right statement, will put on the screen exactly right, just below the arrow, if the student in fact says something like this. It also, there's a wrong statement here. It is a, ignorable word, square. And it says, in that case, it would say, count the sides, and you're still at that arrow and can erase and change your answer. So there's a tremendous amount of stuff built into here, but represented in an extremely compact way to raise the efficiency extremely high for people who are writing materials. And when you run this program, I've typed in a square, and it outputs count the sides, and I have to try again. And now I've written in a wrong tringle. And it's put X's under wrong, because that word shouldn't be there. A, it's left alone because that was listed as an ignorable word. There's a little triangle there saying that there's a missing word between wrong and tringle. And tringle is underlined because it's misspelled, and it says no. And all of that was done by Paul. And it's a splendid example of the flexibility he built in for judging student responses. And it was almost surely unique for the time. And very, very writable, and by ordinary people who knew the teaching but weren't computer experts, but became so as a result of having this magnificent tool. And in fact, one way of characterizing this whole judging business, which included not only words, sentences you see here, We could handle algebraic statements as well as numbers, as well as expressions, scientific units. We could tell you, no, if you wrote kilogram meters per second, but it's really kilogram meter per second squared. We could actually check for all of those things. We tried to identify, judge was the word, concepts more than answers. And that led to great flexibility. So this was a huge step forward, and I should pause here to say a few more words about what this led to. Don had established a very clear, simple, compelling mission statement. We're going to build a system that delivers high-quality, computer-based education with graphics and fast response. And that was figuratively on the wall, and a large number of people could work toward it almost independently because it was so compelling. It's a little bit like Kennedy saying, we will go to the moon, and then a lot of people scurried around and we went to the moon. Another example, more contentious, is we will build an atomic bomb. And Oppenheimer had attracted talented people who scurried around and all worked toward that very, very simple, straightforward mission statement. Well, Don's mission statement was very clear, very compelling, and extremely difficult to implement. And once you have built something that can do this, you can do much else. And you will hear this afternoon about the games and the community and the group notes and the email and all those things that flourished, because although the underlying foundational stuff, including Tudor, was written as to be efficient in assembly language, about 1 million lines of assembly code, more and more of the system software itself was written in Tudor, because Tudor was so fantastically capable and you could write things so quickly. Late in the time I was there, around 84, just before I moved to Carnegie Mellon, I had a visit from a young man who had been working in another place that was doing courseware development. And the environment he was in was a very structured one. There were teachers who were supposed to not know anything about computers, who would design some sort of an educational activity, but they were kept very far away from the computer so as not to contaminate their thinking. This was handed to an educational designer who knew education, perhaps didn't know much about the domain. If he did, that'd be good, but wasn't necessary. That person would massage this stuff to pass it off to teams of undergraduate programmers writing in Pascal. And this was considered to be a very efficient assembly line means of production. The result was that from the time of the initial idea to actually seeing its first draft implementation was 6 months. Now this young person came to our lab, and I acted as a secretary as he told me what to do, because he didn't know Tudor, so I played secretary for him. And he told me about this thing that they had an idea, but they'd never gone through the assembly line, they'd never implemented it. And he sat there beside me as I used the kind of tools I just showed you, making the graph displays using a graphic display editor, using the Tudor language. And in an hour, we had a very complex educational activity that would have taken at least 6 months in his period of experience. And he was just absolutely stunned and floored. And I should also mention something to which Michael alluded. This code that you see at the bottom of the screen went through what you might call a compiler, but it was not exactly a compiler, and yet Tudor wasn't interpreted either, so we used a different name. We said we had a condenser. Now what the condenser did was it knocked down draw, at, right, arrow, answer, right, wrong, right. Those were knocked down to single bytes, basically, describing which of the commands. Well, it would have been 2 bytes, I guess, because there were a lot more than 64 commands. And at execution time, a lookup table was a branch table. You pick up that command number and branch to a routine that would process the arguments that are shown at the right. So You could say Tudor ran interpretively, but it was running off bytecode, so that was already pretty efficient. Moreover, while you see in this simple case just literals like 1911, 2411, those could be full expressions. And those expressions are actually compiled to machine code. And so what the, quote, interpreter did, and interpreter isn't even the right word for it, was when it got to a piece of machine code, it would actually jump into that machine code, execute machine code at full machine speed, pretty well optimized, and the last instruction in that link, in that expression, was a branch back into the interpreter. So you can see why we had to call the tool that went from this source code to the runnable thing a condenser, because it wasn't a compiler and it wasn't an interpreter, it was something, it was a hybrid, like a Prius, and very efficient, like a Prius. I think that's the main things.
A couple quick questions, and I want to give Bob a chance to explain how this was all shepherded into, what we see here, and I think Ray alluded to it last night with the consequences of unintended consequences. In other words, the amazing work that came out of this. We've heard the list: email, instant messaging, essentially. The kind of group dynamics that led to swarming, which led to what we're seeing right now in the real-time environment and social media. All of these things came as a byproduct of the original insights. So is this what led you to jump on this train?
Oh, absolutely. Like Bob, I couldn't not participate in this. I realized that there's two credits I should list here. Paul created Tudor, but he was quickly joined very ably by Rick Bloming. And during the PLATO 3 system, they were the main developers. In the PLATO 4 environment, it got much larger. Many people contributed, way too many to list here. But one of the key players was David Anderson. I also had a lot of work in the computational area, but there were many, many people, and then additional system programmers who are now writing in Tudor, not in assembly language. Mm-hmm. And I also should pay a compliment to the PLATO Services Organization run by Bill Golden, because they created, using Tudor again, a magnificent online manual that was even graphical in its nature and hypertext in many ways. And they also provided, through the communication facilities, online consulting to authors who were far remote, and they could see the screens. And there are people here in the audience who worked as consultants doing that. And that was another major component of this whole environment.
So we've got this thing that, we're standing back from it, and all of a sudden it starts to look like an elephant as opposed to a toe on the elephant. Bob, why did you join up with Bruce, and what was your initial mission, and how successful do you think you were at it?
The experience I'd had at Lawrence Berkeley Lab was with the Control Data 6000 series machines. We used those to process our data. And of course, I was surrounded by a lot of creative, talented people. And amongst other facilities we had there was a vector graphics display device. So before coming to PLATO, I'd actually worked with putting graphics displays together. Seeing what Don could do, what Tudor could do, was just totally amazing, because I knew how much time I'd spent doing simple diagrams with the huge rooms full of equipment that we'd had. And on PLATO in Tutor, one could just, and with the display panels, one could just easily do the diagrams that you want.
It's kind of like what's going on here, right?
A few generations removed.
Yeah. So, and what were the bottlenecks?
So one of the things that I knew about was the power of ECS, the extended core storage, and how one could improve the performance of programs by making use of that, Also, I knew about using it as a shared memory between machines. And at the time that I arrived, I think it was the year that we got our second machine, and we had, as the diagram showed, we had an extended core storage as our large shared memory between all of our mainframe processors. And that whole architecture was something that made a lot of sense to me, coming from the programming that I'd been doing. And I could just see that one could really do some wonderful things with this.
Well, how did you marshal these resources? How did you control them so that they could be shared?
Well, the main thing was that we were short, when you started putting many users online, we were short of CPU, we were short of memory. Disk space probably wasn't so much of a problem. The resources in 72 for 500 users, we thought that 2 TIPS, that is 0.002 million instructions, but 2,000 instructions per second was sort of the minimum that you needed to have for a user. And we thought that about 20 kilobytes was the amount of memory that you needed per user. And lessons and programs were about 50 kilobytes. And you try and run those numbers and fit into your, I think initially we had maybe 1 million words of ECS, and we later expanded that to 2 million. Later on, we expanded the ECS by another factor. I think we added 4 million words of what we called auxiliary mass storage. So there was a, thank you, sorry. So the left-hand side is comparing what we thought we hoped we could make do with in about 72. The right-hand side is, if you look around today, what can your personal computer, what's available? And it's not very hard to get a 3 gigaflop processor, 2 gigabytes of memory, and a 50 meg program actually isn't all that big today. That's a factor of 1,000 in the size of the program, a factor of 10,000 in the amount of memory, and a factor of around 1 million in the number of instructions. And those numbers come from both doing more calculation to do what you're doing and using a lot more graphics. There's the final factor of 1,000 in the instructions, and a large part of the memory is because you're actually doing a lot of graphic things in most programs that people use today. The resource management issue, the system was scaled based on the PLATO 3 data with those numbers that we expected to run 1,000 terminals with the machine, with one mainframe, with 2 CPUs, and 2 million words of ECS. That counted upon everybody in a site of 32 terminals, as in PLATO 3, all being in the same lesson. Now, it turns out that maybe on the first day of a semester, all of the students in the classroom are in the same lesson. Although you're probably lucky even then, if you can manage that. But very quickly, people just go off and they want to do the previous lesson, the next lesson, some lesson the controls on the site probably don't let them do arbitrary lessons. Because one of the first things, or one of the early things that was in place at the time that I arrived, the PLATO Service Organization had been monitoring usage of ECS, usage of terminals, usage of the system, and had written some number of lessons to help control that. And various features were added into the system so that control was possible. So that then that was handed off to, for large sites where there was say 30 terminals in a room, there would be one site controller and very likely a person assigned the job of being the manager of those terminals during the peak lesson times, so that they could make sure that if it was time for chemistry, that only the assigned chemistry class students were in there, so then they'd be in a smaller number of lessons, and they were pretty much guaranteed that that lesson would work with the memory and CPU resources that were available.
So were you developing tools to handle the volume as you went? I mean, is that basically what happened?
To handle the volume.
We tried.
Yeah. Yes, obviously we tried. Every time there's a problem, you respond to it. But ultimately, the biggest response was getting another mainframe and adding on the auxiliary mass storage.
So sending Don on the road, basically, is the ultimate response.
Well, the second mainframe was due to sending Don to Minneapolis to talk with our friends at Control Data, who liked the idea. And the same for getting the maximum amount of ECS. The AMS was an idea probably from Don, but Paul Tucker implemented that and used very inexpensive memory technology, memory chips, that were, so that was built, tested, and installed, and any maintenance was done by the engineers in our own labs.
I would like to add that in a very important sense, Paul's invention of Tudor was a disruptive technology within the PLATO project, because many of the data collected in PLATO 3 became invalid when a large number of authors could produce large, complex, interesting, interactive programs which people wanted to use at any time of day. And so just the explosion in the creation of high quality materials put enormous stress on all of these very scarce resources. So it was a big system. It looked expensive. NSF put a lot of money in. CDC put a lot of money in. But on a per user basis, we were really living in an economy of some great scarcity.
So PLATO Notes, what was the impact on resources of that product?
That was written by people using the system. I mean, Dave Woolley, Paul Tensar were involved in that, and
well, but did it drive demand? I mean,
I'm sorry?
Did it drive demand for system resources?
Oh, I see. The program itself was efficient.
Yeah.
I don't recall that Notes itself, I mean, since everybody was in Notes, that was great. It only used one program slot. I mean, if everybody's in Notes, we've only got one program, we have plenty of memory.
Right. Like Gmail, right?
Well,
Okay.
in a sense, I think it actually helped with the problem, because we very quickly got into a situation where if there were problems and issues, the feedback got to the systems programmers very quickly. And that was actually an important feature in terms of continual improvements, some of which were in the nature of trying to do things in a faster way.
Well, we're running out of time here, so I want to open it up for questions if there are any. But while people are coming to the mics, or however this is going to work, okay. I also, before we leave, I would like to find out from each of you gentlemen what it is that you took away from this rich environment, and how have you applied it over your careers. But yes, sir, go ahead.
So for the test and set operations, did you have those in the ECS shared memory? And if so, about what year? If not, how did you handle race conditions? And on branches in Tudor, did you have labels or did you have to use line numbers? And if so, what year did you get labels?
Okay, well, there were a number of questions there. In terms of the test and set, the way we avoided the race conditions was, in essence, by dividing up the tasks. If you might remember, we go back to that thing that showed the executor, the formatter, and the condenser. In particular, all programs that are lessons that were going to be referring to the same common storage in ECS were assigned to a single executor. And since you could only have one person executing in a single executor at the same time, you thereby avoided the test and set sort of circumstance and the potential deadlocks associated with it. I hope that's a reasonable, quick answer to that question. And then there was a question about branching. About branching the if statement.
Sorry.
Yeah.
Label.
I'm not sure I understood, but I'll take the opportunity to say that one of the there are many unusual features of Tudor language and its descendants, including Paul's own rather successful 10-core authoring system based on Tudor, but there are many other descendants. Because of the nature of the educational process and the flexibility that we all wanted in the possible designs of educational activities, Tudor had some very unusual branching capabilities. Essentially, in modern terminology, think of a website where you can easily branch from one page to another, sort of a hypertext thing. That was part of Tudor, because Tudor programs divided up into things called units. And units could be used as subroutines, but they could also be essentially sub-programs, mini-programs, pages they would now be. So we had this, essentially the notion of pages in a programming language at a time when there was no such concept in other programming languages. And you could look on it as being not a very good language design or not clean or something, but it was absolutely essential to do the intricate kind of branching that you need in an educational program, and you might not need in a Gmail.
All right, so where did you guys take this stuff, and what did you do with it in your career? And what are you doing now in your career? I'll start with Bob.
I did some work in file systems while I was working at PLATO, and also just the overall system design led me to a job with IBM in Yorktown Heights at the research division, where we were doing I joined a group doing a system memory project with the concept of this is going to be the ultimate computer and everything will be in memory. And I won't tell you about the problems with that concept, but that was my next step. And then while at IBM, I also spent several years down in Austin working on the PowerPC RISC 6000 project and working on the virtual memory management and file system support in the RS6000 system.
Bruce?
Well, probably the most direct connection for me in terms of my current work or later years was that Paul showed me the value and the importance of creating a programming environment within which ordinary people could do extraordinary things. And so my own involvement with David Scherer and Ruth Shabai with VPython, which is a programming environment in which ordinary mortals can do 3D animations, which come as a side effect of writing code, is in direct line of Paul's vision that it should be possible for ordinary people to write programs without the intercession of a blessed system programmer.
Michael?
Well, I would say the most important thing I've taken to my current work, and I do now web-based interfaces to large databases for the most part, and also some decision support system things, is in dealing with a client, you want them to, you really got to talk to them carefully and want them to understand there are a lot of different ways to skin a cat. Now, if your client happens to be the ASPCA, you don't necessarily want to put it in those terms, but it's working with people to understand that there are a lot of possibilities they may not have thought of. And what's really important is to determine what their mission, what their goal is at a fundamental way, rather than they say, I want you to write me an X and a Y and a Z and make it happen, but rather to understand what are you trying to achieve. And now let's talk about how to get there.
Yes, go ahead.
This question is for Bruce. You talked about the many descendants that Tudor had. What, right now, is there anything that has the answer judging capabilities and that is in general use and is even on the internet at the moment? What would you say? If somebody was looking for Tudor-like answer judging, where would we go?
I'm actually not aware of anything currently in existence. Paul, do you know of one?
That's it.
Well, to put it another way,
Well,
to put it, just, can we pass the mic around so that people
Can I
can?
comment on one thing on the answer judging? This was at a time when you typed in answers on the computer and you forced people to think. It wasn't multiple choice. You said, what do you want to do next? Say in a chemistry experiment, and then said, well, I want to mix it with alcohol. And then the computer would give a response. That's so different from today. You're working really in a multiple choice world. You're clicking on things where the answer is right there. There's not much thinking, I think, going on right now. And I think answer judging, no one's typing in answers. So why do you need that answer judging that I created back in the 60s? Is that an acceptable answer? I don't think so, but maybe 50 years it'll come back to having people think and write. And, you know, the average person can't spell now, much less type in word answers.
All right, well, we've got 5 seconds, so anybody else? Yeah, let's try and make this quick.
Yeah, I can make this quick. CDC had its own operating systems back then on the 6000 series, Kronos and Scope. How much of that did you use? Were it all homegrown, or did you take some of Greg Mansfield's stuff, or how did this work out?
PLATO 4 ran on top of Scope.
But from my point of view, we booted under Scope, but a few microseconds later, we took over the whole machine.
Well, yeah, it's true. I mean, the allocation of those resources was entirely in the hands of code that we wrote ourselves. Yeah.
All right, well, we're getting the hook here, so
Yeah.
I want to thank you, gentlemen. This has been really interesting.
Well, thank you, Steve.